This is the final section that we will cover in Chapter 4, and it is Section 7.7, Fluid Pressure and Fluid Force. Fluid pressure is the force per unit of surface area. So we can use this little formula here, saying that fluid pressure is equivalent to weight density times the depth. And in this work, it will be referred to using these variables here. One thing you may know is that fluid pressure increases by depth. So the deeper the object, the more pressure there is. And I think if you ever go swimming or if you're a scuba diver, you are pretty aware of this. Here we have some common weight densities that will be used throughout this section. The most common one that we will be using or seeing will be water. So this is the fluids in pounds per cubic foot. Another thing to pay attention to is fluid force. And fluid force is found by taking the fluid pressure times the surface area that is submerged. So if we break this down, then F, or the fluid force, is equal to P, which is the fluid pressure that we saw in the previous slide, times A, which is the area. Now, we found on the previous slide that P is equal to W times H, which again is the weight density and the depth. So WH times A, the density is W, the depth is the height, and A is the area. So the formula that we will use is often this one here. So here we come to our first example, and it says the area of a top side of a piece of sheet metal is 8 square feet. The sheet metal is submerged horizontally, so it's flat essentially, in 8 feet of water. Find the fluid force on the top side. So the fact that it is being submerged horizontally is important because we will see what happens when objects are submerged vertically. It's something different. So in this case, we're going to use the information that's given to us above, where the fluid force is equal to the fluid pressure times the area. But again, we know that the pressure is equal to the weight times the depth, and that will be times the area. So when we are finding this force, we need to know what the density is, or W. Well, the density here is what the fluid pressure is with water. And from our previous slide, you should find that the fluid pressure of water is 62.4. So this is going to give us P. So we will take 62.4 times the height, or the depth of the water. The depth of the water is 8 feet. So together, this is P. Now we need to multiply this by the area of the sheet metal, and the area is 8. So when I multiply all of this, I get 499.2. Now over here, remember that the fluid pressure is measured in pounds per cubic feet. So if I want to include the label for this, I certainly can. This is pounds. This actually becomes pounds per square foot because this one here is pounds per cubic foot. And this one, this is the depth, which is feet. So this foot cancels out one of these, giving me this. Then if I multiply this by the area, which is square feet, what happens is basically these labels cancel out and it helps you find the force or the fluid force here. When I multiply 499.2 times 8, I get 3,993.6 pounds. And that is the fluid force on the top side of this piece of sheet metal. Now, as mentioned, things get more complicated when we are submerging some item vertically. The reason for this is because if an item is submerged vertically, then the pressure on the object varies depending on the depth of that portion of the object. So what we do is we take force on a slice, and it's basically the same thing as before, the density, depth, and area. But what we want to do is just kind of take just a piece of it. So if I break this down, this is the formula we'll use. So F represents force. Once again, this W is the density. This here is the depth of the object. This is the length of the object, and this is the width. Now, the other thing to pay attention to are the limits of integration. This here is the depth of the submerged object, and it's essentially the top and bottom of the object. So the lowest point of the object and the highest point of the object. So let's see how we are going to apply this equation here. In this example, it says find the fluid force on the vertical side of the tank where the dimensions are given in feet. Assume the tank is full of water. So it's helpful to know that the tank's full of water so we can identify the density here. Again, just like we did before, it's 62.4. All right, so let's just jot down that formula that we had on the previous slide so that we can identify everything that we need. Now I want you to notice that everything in this formula is in terms of y. The reason for this is because we are dealing with a vertical submission, and vertical measurements are y values in this case. So we already know what W is. W, we know, is 62.4. But everything else we need to find. So the first thing I would recommend doing is placing a coordinate plane here on our object so we can see what's happening. And if this here is 2, this is implying that the radius of this semicircle is 2. So we know this is 2, -1, -2, 1, and -2. So we should be able to go ahead and figure some information out. Now the h of y, that is the depth. So the depth is equal to h of y. So let's identify what the depth is here. Now if this is 0, then this here, if I draw in some rectangle, or I guess we don't need to draw in a rectangle, oops. But if we draw in something, the height varies in all these different places. Okay, so if the height is varying here, that means the y value is changing. Okay, so this is a y value. We're going in a negative direction. So h of y is represented by negative y since it is below the x-axis. Now the more tricky thing to come up with is the length, or L of y in this case. So the length varies. So if I have this rectangle in here, the length will be changing, okay? But it's important to notice that this is a semicircle. So this distance here from the y-axis over, this is an x value. Okay, so if I want to find the equation of a semicircle, you can start off with the equation of a circle, which is x squared plus y squared is equal to 4 because my radius is 2. I know that everything needs to be in terms of y, so I need to get x squared by itself and eventually x by itself. So if I have x squared is equal to 4 minus y squared, then I can take the square root of that. So x is equal to plus or minus 4 minus y squared under the radical. Now let's address this for a moment. Now, right now, I've just found this distance, which is x. And this is the positive side. So really, this is the square root of 4 minus y squared. Well, I have that same distance over here. Same thing. So I'm going to multiply this by 2 because I have 2 of those values. So the length is 2 times the square root of 4 minus y squared, which is the equation of that semicircle. So we have w, we have h of y, we have L of y, d of y, that's just my width, that's the change in y, my limit of my variable of integration. The only other thing we need are my limits of integration. Now, if I look at this object, this semicircular object is being submerged from here to here. So we are going to integrate from -2 to 0. Okay, so let's set up our integral. The force is equal to 62.4 times the integral from -2 to 0 times h of y, which is negative y, times 2 root 4 minus y squared dy. So one thing I want to mention is that you will only be required to set this up on a test. So if you can get to this point, fantastic. Once you integrate this, you should end up getting 62.4 times 2/3 times the quantity 4 minus y squared to the 3/2. Evaluate this from -2 to 0, and you should get 332.8 pounds of pressure. Here's the last example. In this problem, it says find the fluid force on a vertical plate submerged in the water where the dimensions are given in meters and the weight density of water is 9,800 newtons per cubic meter. So now we're just dealing with a different measurement for weight density. Fine, no big deal. So I think that if you look at this picture here, you might be able to visualize it a little bit better. Basically, we're taking this rectangular object and submerging it in the water vertically. So it's helpful to come up with some coordinate plane to rest this in. And I think it's helpful to utilize the origin a little bit. So I'm going to let this be the x-axis and this be the y-axis. So looking at this, I am told that we are submerging this, and this is the like the surface of the water. And by looking at this, I can tell that this is 6 because 5 plus 1 is 6. We also know that this is a distance of 1 or a length of 1 here, which is important. So let's write our equation again that we used on the previous slide because it's the same thing. And we need to be able to identify each of these pieces in our integral. So let's see. In this case, we know what the weight density is because that's given to us. So this is 9,800. Then h of y is the depth, remember. So we need to figure out the depth of this object. So now the depth of this varies a little bit. So we need to be cautious that the depth up here is different than the depth down here. So when I'm finding h of y, think of, or the depth, let's call this the depth so you know what I'm talking about. We are going to think of it as top minus bottom. So the top is the surface of the water, which is 6. So we're going to represent this as 6 minus y. And this will be the height at different places of this object. Okay, so that's h of y. Then we also need to find the length, which is L of y of this object. Well, looking at this, the length of this object is 1. That does not change, so that's pretty straightforward. The only other thing we need to do is identify my limits of integration. So the limits of integration, that is found by identifying where the top of the object is and the bottom of the object that is being submerged. So remember, this is the x-axis, so that's a y value of 0. We can see here that this is 5 units long, so we will integrate from 0 to 5. So when I set up my integral, I end up with 9,800 times the integral from 0 to 5 of the depth, which is represented by 6 minus y, times the length, which is 1 dy. Again, if you can do this on a test or quiz, you will be in good shape. But once you integrate this, you should end up with 6y minus y squared over 2. And then evaluate this from 0 to 5. And this will give you a result of 171,500 newtons. And that concludes Chapter 7.